What makes a swinging pendulum predictable? And why do long pendulums swing slower than short ones? It's not just because of gravity. It's also because of how simple harmonic motion works and a secret connection to springs. In this video, we're looking at three things. First, under what conditions is a pendulum simple harmonic motion? 2. How frequency and period works. Why timing depends on length, not mass. So the big idea is that the restoring force in the pendulum, the restoring force is the force that tries to bring it back to the center. The restoring force, which for pendulum is gravity, is not constant, because the further you are from the center, the harder your restoring force is going to pull you back. But when it comes to small swings, so not large swings, when it comes to small swings with a small angle, pendulum motion is functionally identical to simple harmonic motion spring systems. I'm going to do some math, some deriving. If you don't care, you can skip ahead. And the goal for this derivation is to show that pendulums at small angles are the same as simple harmonic motion oscillations. Step 1. The restoring force for a pendulum is equal to the y component of gravity. That's what pulls it down. But it's not quite simple harmonic motion, since sine is a curve, and simple harmonic motion, it's up and down or back and forth. So that's where step 2 comes in. When your angle is under 10 degrees, sine of that angle is roughly equal to that angle in radians. So that means, step 3, the force is proportional to the angle. What's that mean? This is just like simple harmonic motion. So for example, your spring, when you stretch it really hard, it's going to yank back harder. It pulls back based on its stretch distance. That's the structure of simple harmonic motion. But there's a problem. This is an angle, and we want distance. Time for the mathy part, which is step 4. The arc length is equal to the distance, which is equal to the length times the angle. This is the kind of stuff we were seeing in rotational dynamics and angular quantities. We can isolate this angle here. Here's what we get. Angle is x over L. And look back at step 3. This equals this. So the restoring force is proportional to negative x over L, or we could just say it's proportional to negative x. Distance is no longer an angle. This is not an equation. This is proportional. It's tied to it directly. So that's how we went from this to this. Next step, with this knowledge here, look at Newton's second law, F equals ma. Because F directly scales with acceleration, that means acceleration is also proportional to the displacement from the center, x. Guess what that is? That's the definition of simple harmonic motion. The further you are from the position of equilibrium, the harder you get pulled back, the higher the acceleration. So for small angles, it's simple harmonic motion, pendulums. And on the free cheat sheet in the description, there's also these two formulas for you. The time for a pendulum is 2 pi length over gravity, and the frequency is 1 over 2 pi, or gravity over length. These are some useful pendulum equations. Before we solve the problem, let's do a key takeaway thing. Mass is irrelevant. Like you saw in those formulas, it was stuff like L over G, 2 pi. Mass was not present in that equation. It doesn't matter. The pendulum equations for timing and frequency don't care about mass. 2. Small angle approximation is critical. 3. Pendulum simple harmonic motion breaks down for large swings. So when the angle is too big, our equation doesn't hold. And here's how we're going to solve our problems. Here's the mindset we're going to have. Shorter pendulums swing faster, and timing is predictable. That's why pendulums are used in clocks. Here's our problem. We're at a science park and they're holding an exhibition. There's a huge pendulum swinging back and forth from a 35-meter tall structure. A student times it as it swings back and forth, and he finds that in 11.9 seconds, it swings 5 times. Our goal for this problem, estimate the acceleration due to gravity. This is kind of a trick problem. I'm going to solve it and I'll show you why. The cheat sheet is going to help here because we're going to be using all the formulas we were talking about. Each swing is a full cycle. So that means the period for one swing would be 11.9 over 5. That's how we find the period for one swing, which is 2.38 seconds. That's nice to know. We're looking for the acceleration due to gravity, 9.8. And the formula that includes G, which also links everything else that we know, like length, period, is the pendulum period formula. Also on the free cheat sheet. And we can rearrange for gravity with our excellent math skills. We rearrange stuff a lot. Math skill is super important. The super is a superpower in physics. So, your new equation for gravity looks like this. We can plug in our values because we know length, 35, and we know time, 2.38. And gravity acceleration should be 9.8, but this problem shows it's roughly 24.4. That's too high. Because in reality, pendulums need small angles for our formula to work. We can't treat it like simple harmonic motion. This means that it was swinging at too large of an angle. So overestimated the power of gravity. Real measures will find gravity is 9.8. This makes studying 10 times easier. Go download the free cheat sheet in the description and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.